Let's do some rotational inertia problems. First one, we'll have the ring, the disc, and the sphere rolling down the ramp. Who wins the race? Well, if you watched the video demo, you saw that the sphere won. Why? Well, let's look at the coefficients. The rotational inertia for a ring is mr squared. We can imagine that there's a 1 out in front. All of the mass is at the full radius. When it rolls, all of the mass has to make that full circumference. The rotational inertia for a disk is 1/2 mr squared. Why? Because not all the mass is at the full radius. The mass is distributed throughout. The mass near the center makes a small circle, and that requires less effort. There's less inertia because they're making a smaller circle to rotate. Well, how about the inertia for a sphere? It's 2/5 mr squared. Now, this certainly looks like a disk, but remember, it's three-dimensional. The axis of rotation is going this way right through the middle. Let's compare this to a sideways diagram of the disk. This is the axis of rotation for this disk. And here it is for a sphere. Imagine both of these objects are rolling towards you. What would we do to a disk to turn it into a sphere? We'd have to take some of this mass and bring it down towards the axis of rotation. That's why the sphere has a smaller coefficient than the disk. Well, does the mass or the radius affect which wins? Again, if you saw the demo, the answer is no. This is similar to when we dropped the two different sized balls and said which one hits first. Well, the mass didn't matter because even though this one has more force, it also has more inertia, it's harder to move, and it canceled out. So we say the mass cancels out. But what about that radius? The larger object would have a larger radius. And you might say, well, that means it's got further to go for that mass on the outside. That's true, but there'll also be more torque. And the radius cancels as well. We're going to see a proof for this later on. But for right now, for the race down the ramp, you need to know it's the coefficient that matters. Okay, here's a problem. We have a ring with a mass of 5 kilograms and a radius of 10 centimeters. It's mounted on a massless, frictionless turntable, and we're going to pull with a string with a force of 4 newtons. And let's exert this force for 7 seconds. Let's first find the torque applied to the ring. Now, pause the video and try to solve this without seeing how I do it. The torque can be found from a force perpendicular times a radius. The string is pulling with 4 newtons, and that's perpendicular to the radius of the ring. Remember, we measure the distance from the pivot out to the force. Let's find the inertia of the ring. It's going to be mr squared because all the mass is at the full radius. And we get 0.05 kilogram meter squared. Now we can find the angular acceleration of this ring as the string unwinds it. We're going to use Newton's second law for rotational motion. Torque equals I alpha. Plugging in the values, we get 0.8 radians per second squared. Now we can find the final angular velocity. Using our definition for alpha, the initial angular velocity is 0, so this is what we have. Plugging in the values, we get 5.6 radians per second. Now we're going to ask what the velocity tangential would be out the edge of this ring. Well, that would be how fast my hand would have to be moving to keep pulling that string. Omega times r equals v. Well, we're going to be speeding up. So at 7 seconds, this would be the omega final, which is 5.6 radians per second multiplied by the radius, and we get 0.56 meters per second. Now, all of this is theoretical. If we do a lab, we're going to expect some variations in our results. Well, here's an experiment. Let's find the inertia of this turntable. It's made of a can on a spinner, the fidget spinner. We're going to wrap the string a few times and have it go to a 15-gram mass that's going to fall. The radius of this can is 6 centimeters. While the string unwinds, the can will complete 2.5 rotations in 3.2 seconds. Can we find the inertia of the turntable? Well, you might want to say I equals 1/2 mr squared, but we can't apply that here. Sure, the can looks like a disc, but there's a spinner underneath there with a weird shape, and we don't have the mass of this object. So how are we going to get I? We have to do it experimentally from this data. We'll say torque equals I alpha. The torque is a force times the distance perpendicular. Well, what's the force? It's the tension in the string. That string is attached to the falling mass. It weighs 0.147 newtons. Because this mass is small, the can doesn't unwind quickly. This is not going to fall very fast. So we're going to make the approximation that the tension is equal to mg. Filling in the data, we can get the torque. We have 0.00882 Newton meters of torque. We're looking for I, so we need to get alpha. We can say theta, how many times it rotates, is equal to 1/2 alpha t squared, plus the initial angular velocity times time. We did the lab from rest, that goes away. Well, the angle is 2 pi radians for every rotation, and we completed 2.5 rotations. This occurred in 3.2 seconds. This gives us 3.07 radians per second squared. All right, we'll remember the inertia of the turntable, put it up here. And now we have experiment 2. I put another can on top of the first can. The radius is 6 centimeters, same as before. The mass, now we can measure this. It's 1.25 kilograms. It's going to be considered a disc. Now when I let the thing go forward, it goes through 2.5 rotations in a longer time. That would make sense. 4.4 seconds. Let's find the inertia of the whole system experimentally. It's still the same falling mass. We'll still have the same torque. We'll find the alpha experimentally. Using this formula, we can now solve for alpha. Plugging in the data, we get alpha to be 1.623 radians per second squared. And we get 0.00544 kilogram meters squared for the inertia. That would be of the system. So here we have the inertia of both objects together. There's the turntable. What do? And here we have I for the disk on top, 0.00257 kilogram meters squared, which is experimental. Now we can compare it to the theoretical. Plug in the data, and we have 0.00225 kilogram meters squared. Well, as you can see, we're pretty close, but the experimental is a little bigger. Now, why? Probably because there's friction here. Friction would lead you to believe that there's more inertia. It would be harder to move. And that's about a 14% error. Now, not everybody did an experiment where the string was wrapped around an outside edge of a can. Some people used a CD disc mounted on a bottle cap on top of the spinner. Well, the difference between these two is the radius where we apply the force. When the string was wrapped around the tuna fish can, the radius was 4.2 centimeters. Some of the bottle caps we were using had a radius of about 2.1 centimeters. That's going to make a difference when you calculate the torque. In both cases, the string is pulling perpendicular to the radius. But obviously, this radius is a lot smaller, and you need to be careful about that. So here's a theoretical problem. We have a ring, and we have the radius is 9 centimeters and a mass of 4 kilograms. You could do the theory and calculate the inertia. The string is going to be pulling off the axle with a radius of 3 centimeters. We have 100 grams out here. Find alpha. Now pause the video, try to do it. Now that's 100 grams, and you might think it's going to fall quickly, but that's a 4 kilogram ring. It's not going to go that fast. So we'll assume the tension in the rope is 0.98 newtons. Start out with torque equals I alpha. The torque will be the tension times the radius. But which one? Well, just look at the picture. The force is applied at this radius, not at the edge of the ring. So we have 0.98 newtons times 0.03 meters. We know for a ring, I equals mr squared. We have the I. Now we can solve for alpha. And we have 0.907 radians per second squared. Now we'll find the acceleration of the hanging mass. Well, you know alpha times r equals acceleration tangential. But what r? Look at the diagram. We have a big R, we have a little r. Where's the rope? On the little r. And that rope will be fed out, which will make this weight fall. So we take the alpha and multiply it by the small radius. And we get an acceleration of 0.027 meters per second squared. That's how fast the weight's dropping while this thing unwinds. Notice how small that is. Yeah, it's because this radius is very small. Watch all the videos, practice the worksheets, read the chapter notes. Good luck.